Listen to this thought and feel the calm chill that follows it. What if the faint traveler we call 3-Eye Atlas is not simply passing by, but pausing to watch? What if it is not a comet at all, but a patient instrument from somewhere older and wiser, drifting like a lantern between the stars while we sleep beneath our own sky? If you enjoy late-night journeys like this, please tap like and subscribe so you do not miss the next quiet exploration. Your small click helps more people find these calm documentaries, and it truly supports the channel. Now let us drift together. Picture the darkness beyond Neptune, where sunlight thins and the planets turn to cold sparks. Out there, a dim object slides along a steep path that does not curl back around the Sunday. Its road is open, the mark of a visitor from far away. Astronomers label such wanderers with a simple code. The number tells us it is the third confirmed interstellar object. The letters point to the survey that raised the first alert. Atlas is a set of robotic telescopes that watch the sky for change, catching brief flashes and slow movers alike. When they noticed this one, the message was simple. Something from beyond is here again. We have welcomed visitors before. The first was a long, dark shard named ʻOumuamua, a strange body that nudged its speed in a way that still inspires debate. The second was a true comet called Borisov, with a tail like a pale brushstroke and behavior that matched the textbooks. Those arrivals taught us something simple and deep. The space between stars is not empty. It carries fragments, snowballs, and perhaps, one day, artifacts. So when a third guest appears, curiosity grows bold. What if this one is not debris? What if it is a device that uses debris as clothing? This is where the Black Forest theory enters. Some also call it the dark forest idea. Picture a vast forest at night. Every creature avoids the light because light gives you away. Every campfire draws attention you may not want. If life is spread across the galaxy, every civilization may learn the same lesson. Stay quiet, watch from the shadows. If you must look, use tools that seem natural, so you do not reveal yourself. In such a cosmos, the safest eyes are the ones that pretend to be stones. A comet is the perfect mask. It is common, it makes no sound, it follows a path no one controls, it sheds a cloud of gas and dust that can hide whatever sits at its core. If you wish to study a young world without being noticed, you might send a probe that wears a comet like a coat. You would nudge its route so it swings close, gathers whispers of radio noise, faint glints from our night side, trace dust from our upper air, and then slips away. To any telescope, it would look ordinary. To you, watching from far away, it would be a quiet scout with a clear job. We must be careful. This is a possibility, not a claim. The strength of science is that it asks for evidence and welcomes tests. The gift of imagination is that it suggests which tests to make. Tonight we will balance both. We will drift through what is known and wander through what might be. We will ask why 3-Eye Atlas brightened when it did, why its path looks the way it does, and which natural forces could paint the same signs. We will also ask what an intelligent scout would do if it wanted to hide in plain sight. Let us keep the language easy. An interstellar object is one that does not loop the Sunday. It arrives from outside and leaves again. Astronomers can tell by the shape of its path and by its speed. When the curve is open instead of closed, we call it hyperbolic. That word only means the visitor will not stay. Think of throwing a ball so hard that Earth cannot pull it back. That is the idea. No heavy math is needed to follow along. Now the brightening. Comets often shine more as they warm because sunlight turns ice into gas, and the gas carries dust that reflects light. There are rough patterns for how fast that glow tends to grow. When an object brightens faster than expected, we ask why. It could be a fresh patch of ice turning toward the Sunday. It could be a fragile crust that cracks and vents like a geyser. It could be fragments breaking away and exposing more surface. All of these are simple, natural things. Yet, if the glow climbs in sudden steps, if it changes in ways that line up with certain angles to Earth, or with passes over our busiest regions of space, then curiosity has a reason to lean forward. The Black Forest idea warns us not to expect loud signals. In a quiet galaxy, the wise move is to blend in. A watcher would avoid radio beacons and bright engines. It would choose patience. It would ride a platform that locals expect to see. It would linger near the lanes where young civilizations tend to aim their deep space craft, because engineers repeat what works. To test that thought here, we can place the visitor on a simple mental map of our own routes outward. Where do our probes travel? Which directions do our high-gain antennas point? Does 3i Atlas pass near those lines, or pause when Earth is listening hardest? We will not leap to answers. We will simply compare. Notice the feeling all of this evokes. It is not fear, it is the deep alertness you feel when you stand in a dark forest and realize you are not alone. The branches do not move, the wind is soft. Somewhere, eyes watch. Maybe they belong to an owl. Maybe they belong to something you will never meet. You are safe, but you are awake. That is the tone we will keep together. Calm, curious, unafraid. In the next part, we will slow down and listen to the discovery itself. Who first saw the motion, how the alert spread, what the earliest measurements said. We will place each piece on the table and trace a picture anyone can follow, one step at a time. Then, we will set that picture beside the quiet logic of the Black Forest and see where they agree and where they do not. For now, breathe with the rhythm of the stars outside the window. The visitor drifts. We watch. And perhaps it watches too. First came a quiet ping in a database. Atlas, the night watch of small robotic telescopes, compared one frame of stars with the next and found a dot that had shifted in a way that did not match the usual parade of near-Earth rocks. The software flagged it. A person checked the frames. The motion was slow, steady, and a little unusual. A short report went out to the people who coordinate new object alerts. Within hours, other telescopes were turning to the same set of coordinates to confirm the find. The first confirmations are always simple. Is it real? Is it moving? Does the motion fit with an object bound to the Sunday astronomers mark the points on a sky map and let a program fit a curve? When the curve opens instead of looping, a whisper passes through the room. We have another traveler from outside. The official label follows a clear rule. The number marks it as the third interstellar object. The name points back to the survey that saw it first. 3i Atlas is neat and short, but the moment it represents is large. Once again, something from beyond the neighborhood has wandered into view. After discovery comes the rush to measure light. Even a faint smear of brightness carries clues. Observers take many short exposures and stack them to make a cleaner signal. They measure how the light changes night to night and how it spreads from the center to the edges. If the middle is sharp, the object may be rocky and bare. If the light has a soft, fuzzy halo, it is likely blowing out gas and dust, the signature of a comet waking up. Early notes on our visitor lean toward a soft profile, hinting at a coma, the hazy shell that forms when ice is warm and release vapor. Nothing shocking there. Many interstellar fragments are expected to be icy at heart. As more data arrived, the orbit took shape like a pencil drawing that gains weight with each stroke. The path was hyperbolic, which simply means the object would not stay. Its incoming direction pointed from the deep background where nothing in our system lives. Its speed, while high, matched what you would expect for something falling inward from the quiet darkness between stars. This is comfort to those who favor natural origins. So far, all the pieces sit where physics says they should. Yet a fresh discovery always leaves space for wonder. People watch the light curve for surprises. Does the brightness rise smoothly as the sun heats the surface, or does it jump in steps as if vents turn on and off? Are the color tones steady, or do they shift in a way that suggests new material being exposed? Does the object flare after a turn that points a new face toward sunlight? These questions sound technical, but they are only careful ways of asking what any curious mind would. Is this behavior ordinary? The answer, as usual, is mixed. Some nights, the glow climbs, as predicted for a small comet. On others, the increase is a little faster than the rule of thumb. Natural reasons are ready at hand. A fragile crust can break and reveal fresh ice. Fine dust can clump and then let go, sending a temporary veil around the core. Small fragments can peel away, raising the reflective area for a time. All of these happen quietly, without drama, and leave nothing but a gentle rise in brightness. This is also the exact mask an intelligent watcher would want. If you were hiding in plain sight under the logic of the Black Forest, you would choose the slowest, softest changes possible. You would time any turn or tiny thrust to look like sunlight did the work. You would let ordinary comet physics cover your tracks. A subtle attitude change could present a new radiator panel to the sun and also a new sensor face to Earth, while to us it would look like a crust crack that vents briefly and then fades. A small outgassing event could be both a cooling maneuver and a signal that gathers more dust to thicken your cloak. So the next line of inquiry goes to motion. When gas jets out, it pushes a comet a little, like air escaping a balloon. Astronomers call these small pushes non-gravitational forces. They can be measured if you track the path closely over weeks. If the object drifts off the path that pure gravity predicts, you can model how strong the gas jets must be and in which directions they act. For a natural comet, the pushes usually line up with sunlight. They rise as the object warms and ease as it cools. If the drift grows when sunlight is weak or points in odd angles, the eyebrows go up. Gathering that level of detail takes patience, many telescopes, many nights, a shared ledger of positions, and careful math. The early fit for 3i Atlas did not shock anyone, but that does not end the story. As more points join the chain, the model sharpens. A quiet pattern can come into view. The risk is to read too much into small shifts. The promise is to let the data speak with a stronger voice. Let us keep our feet on steady ground. The people who run the nightly alerts are cautious by design. They have seen thousands of icy wanderers and hundreds of quirks. They know that rare does not mean artificial. They also know that every dataset carries noise, and that 2 nights of odd light can be weather on Earth, not weather on a comet. At the same time, they are human, and wonder lives in them too. No one who studies the sky is entirely immune to the idea that someone else might be studying us back. This is the balance we will ride through the rest of our journey. We will not claim a watcher where a snowball will do. We will not dismiss a pattern just because it is inconvenient. We will listen to what the observations say and bring them beside the quiet logic of the Black Forest. If life is common and caution is wise, then quiet watchers are not only possible but sensible. If the cosmos is random and generous, then icy debris will keep passing by, wearing the same soft halos and leaving the same faint trails in our camera chips. In the next part, we will slow the camera even more and walk through one line on the whiteboard, how a faint point becomes a path, how a path becomes a prediction, how pushes from gas or anything else show up as gentle bends. We will translate each step into everyday language so you can feel the method in your hands. No heavy math, only straight ideas. Then we will ask the question again with a little more steadiness. If something wanted to watch us without being seen, what exactly would we expect to notice? Begin with a single dot on a single frame. A telescope gathers light for a few seconds and freezes a picture of the sky. The stars hold their places like pins in dark velvet. Our visitor is the one point that shifts a little between frames. Astronomers circle that point and write the exact time. They do it again on the next frame and the next. Now the dot is a breadcrumb trail. Turn the breadcrumbs into a path. Picture a clear sheet laid over a star map. Each time mark is a small sticker. Connect the stickers with a thin line. The line is not yet perfect. It is a guess based on a short span of motion. But even a short span reveals direction and speed on the sky. With 3 or 4 points, the computer suggests where the dot will be tomorrow. With a few more, it suggests where the dot was yesterday before we noticed it at all. Now, switch from a flat map to a 3-dimensional thought. The dot is not only crossing our view, it is also moving toward or away from us. Tiny shifts of the background as Earth turns and orbits help solve that depth. Astronomers plug in the times, the positions, and Earth's motion. The math is careful but not mysterious. The result is an orbit, which is a description of the path through space. If the orbit closes like a loop, the object belongs to the Sunday. If the orbit is open, the traveler will not return. Interstellar objects follow open paths. With an orbit in hand, astronomers run time forward. Where will the object be in 2 nights? How bright will it likely appear if its surface keeps shedding dust and gas at the same pace? Observers point their telescopes accordingly. When the dot shows up on schedule, confidence grows. When it arrives a little off, another question appears. Is gravity alone the full story? Gravity bends paths in steady curves. Comets add small pushes when sunlight turns ice to vapor and the vapor jets out. Picture a fine garden hose. The spray nudges your wrist. A comet feels the same nudge. Over days, many tiny nudges add up and shift the path by a whisper. Astronomers call these changes non-gravitational forces. They show up when the actual positions differ in a persistent way from the positions predicted by gravity alone. Light carries matching clues. The haze around a comet, called the coma, brightens as the sun warms fresh ice. Most comets follow a gentle pattern. If the glow climbs faster than expected, teams look for simple reasons. A crust can crack and expose clean ice. A new jet can switch on. A fragment can break loose and add reflective area. Often the light and the tiny path drift rise together, which fits natural venting. Now place this beside the quiet logic of the black forest. In a cautious galaxy, a watcher would hide behind ordinary physics. It would choose a platform that already vents and already brightens. If it needed to rotate a sensor or warm a panel, it would do so when sunlight could take the blame. In our data, that would look exactly like a small bend that points the same way the sun points, along with a small rise in brightness. The mask would be perfect because it would be true. Comet behavior would cover every move a careful probe might make, and that is exactly why the idea is both sensible and hard to test. So how could we tell nature from intent? We look for differences in rhythm, orientation, and opportunity. Rhythm first. Natural jets often follow the object's own day and night. A designed maneuver might happen when Earth is best placed for a look, not when the sun is strongest. Orientation next. If small drifts keep lining up with our planet rather than the sun, that is interesting. Opportunity last. Most comets glide past without caring where our networks point. A watcher might pass through clear lines of sight or linger when receivers are listening their hardest. These checks are simple to run. Plot each tiny path drift against the angle from the object to Earth. Mark each brightness step against the geometry to our radio arrays and common probe routes. Compare the visitor's track to the historic lanes of our spacecraft and the belts where satellites cluster. If patterns do not appear, nature keeps the crown. If a few patterns repeat beyond chance, curiosity earns a closer look. Scale keeps us humble. The pushes are gentle. The distances are huge. Measurements have error bars. A cloudy night can erase a point that would have tied a story together. That is why teams pool data from many observatories and why patience is the best tool we have. For tonight, hold the simple chain of ideas. A dot becomes a path becomes a prediction. Predictions, compared with reality, reveal tiny pushes. Those pushes and the light around them tell a story. Most of the time, the story is ice, dust, and sunlight. Sometimes the story keeps a small question alive, like a quiet rustle in a dark forest. In the next part, we will imagine what a hidden scout would actually measure while staying silent. We will ask what you can learn from a planet without speaking to it. Heat maps, reflected light, radio whispers, trails of dust. Step by step, we will sketch how a full profile of Earth could be gathered by something that never says a word. Imagine a patient scout that never speaks. It turns no beacons on. It burns no bright engine. It lets sunlight do the talking and listens to what our world already gives away. What could it learn while wearing the soft disguise of a small comet? First, heat. Every world glows in infrared. By drifting past and sweeping a quiet sensor across Earth, a watcher could map warmth and coolness. Day and night paint stripes. Seasons shift those stripes north and south. Cities leave hot knots after sunset. Oceans breathe heat with the rhythm of currents. From these patterns you can read our tilt, our storms, and the outline of our climate. Second, reflected light. Sunlight bounces from cloud, ice, forest, sand, and sea in different ways. A calm ocean throws a mirror glare. Rough waves smear it. Thick clouds brighten the disk and hide the ground, while deserts shine pale and steady. Watching Earth brighten and dim as it turns, a probe could sketch coastlines, storms, and the size of polar caps. At night, city lights and fishing fleets draw glowing threads along the coasts. Third, color and air. When sunlight passes through the thin edge of our atmosphere, parts of it are eaten by gases. A simple prism reveals those bites. Oxygen leaves one mark, ozone another. Water vapor and methane add their own. A seasonal swing in some gases hints at breathing forests and oceans. Faint traces of rare industrial molecules, if they exist, would hint at technology. No call needs to be sent. The air answers by itself. Fourth, radio whispers. Earth hums with radio. Navigation constellations tick. Weather radars pulse. Deep space dishes send thin beams toward our probes. Thousands of satellites speak in tidy packets. Most power is modest, but a nearby listener with modest antennas could hear the chorus. From the pattern and the clockwork repeat of signals, a watcher could learn our habits and the way our networks rise and fall with day and night. Fifth, magnetism. Earth has a magnetic shell that flutters when the sun sends gusts of charged particles. Those gusts light our polar skies in auroras and set the upper air to ringing with soft hiss. By listening and watching from space, a silent probe could measure our magnetic strength and infer motion in the hot metal at our core. It would also see how well our air shields the ground from solar weather. Sixth, gravity. Everything with mass pulls on everything else. A patient instrument can feel tiny changes in speed while passing Earth and the Moon. Those changes tell the shape of the combined pull. From that shape you can infer how much mass sits in oceans, mountains, and ice caps. You can even sense the tug of large storms because water is heavy and moves as clouds and rain. No contact is needed. You ride the curve and measure your own heartbeat of speed. Seventh, dust and breath at the edge of space. Earth leaks a few atoms and tiny grains every day. Sunlight stirs a thin skin of gas just above the air. A small sampler could taste that skin while it cruises by. Ratios of light and heavy forms of oxygen and nitrogen whisper stories about climate and industry. Microscopic dust carries traces of rocks and soot from below. Over time, a careful collector could build a diary of our surface without ever dipping a wing into the air. Eighth, ocean shine. The angle of a bright sparkle from the sea tells the height of waves and the direction of winds. Smooth swaths of shimmer show where the water is slick with oil, natural or spilled. Bands of green along coasts swell when plankton blooms. All of this is visible from space to eyes that know how to look. Ninth, the living edge. Green plants reflect near-infrared light strongly. Seen from above, this creates a subtle bright fringe at the border between red and the next band. As continents rotate into noon and away to evening, that fringe rises and falls like a slow meter. A watcher could map growing seasons and feel the health of forests with a daily glance. 10th, our presence in orbit. A passing eye would note belts of satellites, the flicker of spent stages, and the quick scratches of debris that tumble and glint. Transponders blink in regular beats. Tracking radars sweep like lighthouses. Even when single objects are too faint, their group fog reveals a culture that has learned to climb. Put these pieces together, and you have a profile drawn without speaking. Temperature tells climate, reflected light tells surface and weather, color tells air and water, Radio tells habit. Magnetic flutter tells the hidden heart. Gravity tells the weight of ice and sea. Dust tells industry. Ocean sparkle tells wind. The living edge tells forests and crops. Orbit fog tells an age that has stepped beyond the ground. If a careful mind wanted to hide, it would fold this survey into ordinary comet life. Infrared scans would happen while the sun already warms the nucleus. A slow roll to sweep a sensor would look like a dusty jet turning on and off. A pause to listen for radio would arrive when geometry already brightens the coma. Every motion would wear a natural excuse. In the next part, we will let this imagined survey guide our eyes. We will ask what patterns in real measurements would hint at timing or orientation chosen for advantage. We will also set down the natural baselines we expect from a small, icy body, so that any claim of intent must first step over that honest bar. Let the survey shape our questions. Start with timing. A natural comet responds to sunlight like a slow-breathing animal. As it nears the sun, ice is warm, gas lifts off, and the coma brightens with a steady trend. Day to day, small swings track the simple rhythm of rotation and the changing angle to sunlight. If a sequence of brightness steps keeps landing during hours when Earth faces the object with its quietest radio noise, that is a red flag. If the steps tend to appear when our large antennas are pointed elsewhere, that is also curious. Natural behavior does not care about our schedule. A careful scout might. Next is orientation. Gas jets from sunlit cracks act like tiny thrusters. Their gentle pushes usually tilt along the line from the comet to the sunday. Over several weeks, the accumulated drift tells a clear story. If those drifts lean toward Earth more often than they align with sunlight, we take note. A soft pattern is enough to spark study. One odd week proves nothing. 5 or 6 repeats through different angles of the orbit begin to feel like intent. The trick is to check that the effect remains when weather, instrument changes, and data gaps are accounted for. That is why teams share records, compare methods, and try not to fall in love with a result too soon. A third test is opportunity. Our world has busy corridors in space. Satellite belts ring the planet. Deep space dishes in a few countries beam narrow streams out toward far probes. There are windows when these beams sweep near where a passing object stands. A natural body pays no attention. A hidden watcher might choose to loiter for a few extra hours during those windows, then resume its outbound drift before anyone has reason to track it more intensely. We look for slight delays, for gentle turns that keep a clear line of sight when a clumsy path would have broken it. Again, this is not courtroom proof. It is the sort of quiet nudge that makes scientists widen the search. To sift real hints from noise, we need a baseline guide for normal comet life. Here is a simple one anyone can hold. Brightness. Expect a general rise that gets faster as the object approaches the sun and slows as it leaves. Short bumps happen when a crust patch breaks, when the spin lifts a warm area into view, or when fresh dust hangs around the nucleus. These bumps often fade within a few days as the new surface settles or the dust thins. Color. Most small comets look neutral to slightly reddish in visible light because their dust is a blend of carbon-rich grains and rock powder. As they warm, a touch more blue can appear near the core, where gas scatters sunlight. Strong, repeated color swings are unusual and usually mean new material was exposed or the viewing angle changed. Shape of the glow. The coma tends to be round with a soft edge. A faint fan or tail points away from the sun because particles are pushed by sunlight and the solar wind. If short, narrow fans keep pointing toward Earth through different phases of the orbit, that is unexpected. Motion. The path predicted by gravity alone will miss slightly because gas jets push. These non-gravitational drifts are mild, smooth, and they peak around the time of maximum heating. If the drifts peak at odd times, especially tied to Earth-facing geometry rather than Sun-facing geometry, we mark that page. Spin. Many comets tumble a bit. Their day length can change as jets act like tiny brakes or accelerators. Most such changes track the strength of sunlight. Changes that track Earth geometry would be odd. With this baseline, we can build a gentle checklist. Plot the light curve and note bumps. Do the peaks line up with local solar noon on the comet, or with times when Earth presents the wide face of our radio and radar networks? Track the direction of the tiny path drifts. Do they favor the sun, or do they favor our planet? And does that preference hold across weeks? Map the coma structure. Are the fans and bright knots stable in solar coordinates, or do they keep reorienting to keep clear lines of sight toward our crowded orbits? Watch the spin. If period changes sync with solar heating, that is ordinary. If they sync with favorable listening geometry to Earth, that is interesting. Lay the track of 3I Atlas over known lanes used by our deep space probes. Does the visitor pass straight through a zone where we often aim narrowband signals, or is that just our bias seeing patterns after the fact? These are calm tests. None require exotic tools. Most rely on patience and on many pairs of steady hands across observatories around the world. This is good science in a quiet key, the kind that fits a long night and a clear mind. There is another layer, one that fits the Black Forest idea without making it a rule. In a cautious galaxy, the safest move is to appear boring. A watcher that seeks to blend in will accept inefficiency to keep the mask. It will not chase perfect geometry if that risks a sharp maneuver. It will skip a tempting window if taking it would brighten the coma in a way that screams for attention. That means the strongest signs of intent may be weak by design. Patterns will be soft. Alignments will be almost but not quite persuasive. Proof, if it comes at all, will come from accumulation, not from a single dramatic event. That is why our tone stays gentle. Wonder and restraint can share the same seat. The more we test for simple causes first, the more weight any remaining oddity gains. If after many weeks, the drifts still tip toward Earth when they should not, if the light bumps still prefer hours when our big dishes rest, if subtle fans still hold a clear view into our most crowded rings, then we circle those pages and invite more eyes. There is comfort in the other outcome as well. If nothing unusual stands up to patient checking, then nature once again shows her rich variety. A small world of ice, dust, and sunlight writes a familiar poem across our cameras and then heads for the dark. That is a lovely story too, and one that teaches us about the raw material of planets. Let us keep moving. In the next part, we will turn to what a cautious civilization gains by watching this way. What long arcs of time demand such patience? What risks do they avoid by staying quiet? What could they learn about us that a broadcast would never reveal? We will keep the language plain and the pace slow, as though we were walking a forest path by starlight, reading the ground for tracks that may or may not be there. Caution is a strategy born from long years. In a galaxy where light takes ages to cross the dark, haste is costly and exposure can be dangerous. A civilization that endures long enough to reach other stars would likely treat patience as a survival tool. It would gather knowledge slowly, accept small samples instead of quick contact, and prize anonymity the way sailors prize a sturdy hull. The Black Forest idea points to the same habit. If every signal could draw unknown eyes, the wise keep their voices low and their footprints faint. What, then, does silent watching deliver that loud greetings cannot? First, truth unfiltered by performance. When no one knows they are being watched, they behave as they really are. Our energy use, our traffic in orbit, our handling of storms, our cooperation during crises, and our appetite for conflict all reveal themselves with honest rhythm. A careful survey across a few of our years would sketch our cycles of growth and strain better than 1,000 speeches could. Second, safety. Broadcasting is a declaration of position, capability, and intent. It invites a reply from anyone, friend or foe, near or far. A quiet scout trims that risk. It learns where hazards live, which factions control the sky, and whether the target world even tolerates unknown machines. If danger is high, the scout leaves. The homeworld remains a rumor. Third, calibration. Every young culture has different noise and different norms. By listening first, a patient watcher learns which parts of its own technology stand out and which pass unnoticed. It can tune power levels, choose frequencies that hide beneath local clutter, and adjust heat radiators so they glow no brighter than a patch of sunlit dust. Lessons learned at one world make the next survey safer. Fourth, long arc science. A society that thinks in centuries does not rush a single snapshot. It wants climate baselines, tectonic rhythms, and the pulse of biology through seasons. It also wants to model the likely paths of a civilization like ours. Do we stabilize as we grow, or do we swing? Do we protect our biosphere once we see its fragility, or treat it as a storehouse with no lock? These questions are answered by watching the dance of years, not by a brief conversation. Fifth, ethics of non-interference. Intervention can break fragile systems. A broadcast could panic, a landing could contaminate, a gift of knowledge could tilt history. By staying quiet, a cautious culture avoids harm it cannot predict. It lets the younger world choose its own future. If contact ever comes, it can be offered with better understanding and narrower risk. What could a patient survey already conclude about us? From radio noise alone, that we have stitched the planet with networks and clocks. From our satellite fog, that we can build and steer in microgravity. From the heat signature of cities and farms, that we have transformed large parts of the surface. From the chemistry of our air, that we burn ancient carbon and that forests still breathe. From our launches and planetary missions, that we hunger to explore. From military radars and re-entry tracks, that we also fear and prepare. With these facts in hand, what choices might a silent watcher weigh? One branch is to keep distance and file a report. Another is to leave a passive sensor where our own probes will eventually find it, timed to wake only when approached. A third is to run a single controlled experiment, such as slipping through the edge of our magnetosphere during a solar storm to see how our technology reacts. Each path preserves the mask of a comet or a rock because that mask blends with what we expect to see. There are limits to what caution can achieve. Without closer passes, biology remains statistics inferred from color and gas. Without cooperation from our receivers, most of our traffic stays undecoded. Without touching the air, there is no direct sample of microbes or pollutants. The choice to stay quiet accepts these blind spots. That acceptance is a signature in itself. It says the watcher values survival and restraint above complete knowledge. Now turn the mirror. What do we gain by treating 3I Atlas with this dual lens of nature? First, intent as a hypothesis. We gain better data regardless of the outcome. We organize archives more carefully. We coordinate observatories across continents. We test and refine models of comet brightening and tiny jet pushes. If nothing odd remains after that work, we still advance comet science. If something faint but persistent survives, we have a focused case for deeper study when another interstellar object appears. There is also a cultural gain. Wonder kept within reason is a strong teacher. It keeps minds open without making us credulous. It invites more people to learn how we know what we know. It makes the night sky feel near enough to matter, yet vast enough to humble. Consider timescales. Our lives stretch across decades. Civilizations, if they last, must plan across millennia. A quiet scout woven into a harmless cometary cloak can afford to wait out our seasons and our tempers. It can revisit or leave breadcrumbs for successors, faint devices that only wake when warmed by a passing beam from home. If the Black Forest idea describes reality even partly, then patience is not only a tactic, it is a worldview. All of this lives beside the simplest story, which remains strong. A small icy body falls inward, warms, sheds a breath of vapor, glows for a while, and leaves. The slight oddities on its curve are the usual quirks of fractured crust, uneven spin, and sunlight acting on grains too fine to see. The coma's blush is dust, the jet's push is physics. Our task is not to choose romance over reason, or reason over wonder, but to hold both gently and let the evidence nudge us. In the next part, we will place a practical guide beside the observation windows ahead. We will walk through the coming weeks, note the angles when geometry favors clear tests, and explain in plain words what a small anomaly would look like to the eye. With that roadmap, you can follow the unfolding story at your own pace and feel the quiet thrill of tracking a visitor that may be nothing more than nature or something more than we yet dare to say. Here is a simple roadmap for the nights ahead, a calm checklist you can follow with a sky app, a notebook, and a mug of tea. We will mark windows when geometry is kind, describe what a tiny anomaly might look like, and keep every step in plain language. First, brightness watching. Each clear night, note the most recent reported magnitude from observatories. The scale runs backward, where smaller numbers mean brighter light. You do not need formulas, only trend. A natural comet near the sun brightens smoothly with small bumps when fresh ice vents. If on 2 or 3 separated nights the glow rises sharply right when Earth, the sun, and the object align so that Earth is most face-on, jot that down. Natural venting does not care about our viewing convenience. Second, timing against our radio habits. Our largest deep space dishes follow schedules that cluster by local daylight at their sites. When they hand over between shifts or pause for maintenance, the sky near Earth gets a little quieter. If a sequence of brightness upticks or subtle path changes keeps favoring those quieter spans, note the coincidence. The safest way to keep bias low is to decide a rule in advance, such as, if 3 bumps land inside this 2-hour window during the next 8 usable nights, I will flag the pattern for interest, then stick to it. Third, the direction of tiny pushes. You will not measure these yourself, but you can follow expert summaries. Astronomers report the sign and direction of the non-gravitational drift after they fit many nights of positions. When the gentle push points away from the sun, that is textbook behavior for dayside vents. If the derived push angles lean toward Earth more often than chance through very different viewing angles, that deserves attention. One stretch is nothing. A pattern across weeks matters more. Fourth, coma structure. When teams share stacked images, look near the nucleus for faint fans. Natural fans usually open away from the sun like a windsock. If a narrow wedge repeatedly favors the Earth line on nights when the sun sits off to one side, mark it. The word repeatedly is key. A single night can fool the eye. Dust knots drift and processing choices matter. Fifth, spin and day length. Teams estimate rotation by watching how the light flickers as the object turns. Small bodies change day length slowly as vents act like tiny thrusters. If quick changes appear right when Earth geometry improves for listening, write that down. One match is nothing. Several matches, separated by dull stretches, are more curious. Sixth, opportunistic loitering. Track. When the visitor crosses sky sectors, our deep space antennas often use for outbound signals to probes at Mars and beyond. You can find rough plots on public mission dashboards. If the pace seems to slow a little in those sectors and then pick up again afterward, even by a small amount, that belongs in the notebook. Do not predict. Note first, test later. Seventh, special nights. A few dates will make the Earth visitor sun angle ideal for seeing coma structure, or will turn the tail edge on so subtle striations stand out. Mark those nights as anchors. On those windows, a small anomaly is easier to spot, and a lack of anomaly becomes a stronger vote for normal behavior. Eighth, cross-checks. When one observatory reports a flare or a jet, see whether another site saw the same feature within the margin of time expected from the object's spin. Shared features across sites on the same night add confidence. Solo features that fail to repeat elsewhere deserve a lighter pencil. Education changes too. A teacher can hand students a public light curve and let them mark bumps and slopes. A club can mirror professional practice by writing simple rules before the observations and grading claims against those rules a week later. When people feel the weight of a notebook in their own hands, the night becomes personal. interest that might fade after a headline turns into a quiet routine. That routine is the seed of a wiser public. Our instruments expand because we ask kinder questions. What else would help if another interstellar object appears? Wider infrared coverage would track heat better. Polarimetry would tell grain sizes in the coma by reading how light twists on the way to us. High-cadence photometry would reveal subtle spin changes without long gaps. Modest upgrades across many sites often beat a single heroic instrument. Hardware that also serves planetary defense earns lasting support. Policy changes as well. Clear rules for rapid data release and credit prevent hurt feelings when the clock is running. Agreements that let one nation's radar join another's optical campaign produce cleaner results for both. A shared calendar of sky windows reduces pile-ups on the same nights and fills the gaps on others. These are mundane gains, but they hold strong when glamour fades. Culture grows new stories. People of many ages now know that rocks from other stars really pass through our yard. Fiction gains fresh footholds, and some of those tales pull young minds toward engineering and math. Wonder that stays close to truth widens the audience for real work. What about the risk of false alarms? A false alarm handled well raises our skill. It forces clearer models, sharper baselines, and better checks. It also teaches tone. When the public sees experts say "not yet" rather than "never," trust grows. When the public sees experts admit a bias and correct it in the open, trust grows faster. Fold these gains back into our gentle question about a quiet watcher. If such watchers exist, the best response from us is the same as for a natural comet. Watch well, share quickly, test fairly. Build tools that improve even when the answer is ordinary. A civilization that values patience will notice that we value craft. If contact ever comes, it will be easier between cultures that respect careful work. There is also a personal lesson. You can take this night practice and apply it to more than the sky. Plan before you act. Keep your notes steady. Set fair rules. Review on a regular schedule. Accept null results with grace. Many of the pressures that bend research also bend daily life. The same small virtues help both. What might the next steps look like after 3i Atlas returns to the dark? Expect new surveys with wider fields and deeper reach. Expect open catalogs that link light, color, spin, and drift in one place. Expect more small satellites that can snap to a new target within hours and add ultraviolet and infrared views that ground telescopes cannot capture. Expect citizen logs to be archived with simple formats so that quick looks years later can build on the notes of thousands of careful eyes. Expect discussion about how to greet a clear case of artificial origin if it ever arrives. Not a plan to rush contact, but a plan to handle evidence. Who checks the data? Who replicates? Who speaks for the community when the result passes the last hard test? A calm process is part of the signal we send about who we are. In that light, it hardly matters whether 3i Atlas is only dust and ice. The work we do around it builds a better commons. The nights we spend watching teach patience. The spreadsheets we fill teach honesty about what we know and what we guess. The talks we have with friends about what it would mean to be watched teach humility. These are gains that last. And there is still the deep thrill that needs no verdict. A small light slides across the star field and returns, with our help, to a place on the chart. We check the curve, we draw the slope, we adjust the model, and we share. The galaxy is too wide to hold in mind at once, but a single faint visitor can make it feel near. This nearness is a gift. When the visitor fades and our notes close, the sky remains. Another survey frame begins. Another line of code sorts the specs. Another person leans at a window with warm hands around a cup. Curiosity continues as a quiet river. We stand by it and listen. If one day a voice speaks from across the water, we will be ready. If a cautious culture chose to build a watcher that looks like a small comet, what would that machine be like? Keep every part simple enough to hide under ordinary physics, and every move gentle enough to pass for sunlight at work. Start with the core, at the heart, sits a compact platform, not much larger than a small car. It holds the brains, the memory, and the sensors. Around that heart is a shell of rock powder bound with porous ice. The outside is uneven and dull, the right look for a dusty nucleus. A loose jacket of grains trails the surface so that sunlight and gentle vents lift a natural coma with no need for loud tricks. If someone takes a picture, they see what they expect, a fuzzy pebble in space. Power must be quiet. Far from the sun, a few small heat sources the size of thick books can supply steady watts without bright glow. Nearer in, fold-away panels can sip sunlight and yet hide inside shadowed pockets when not in use. Waste heat leaks out through textured patches that blend with sunlit crust. To a telescope, those patches look like ordinary warm spots where fresh ice is turning to vapor. The thermal signature matches the cover story. Attitude control must be gentler still. No fast jets, no sharp turns, only tiny adjustments that ride on natural venting. The platform carries thin channels that route gas from sunlit pores to shaded pores. By opening one channel and closing another, the craft tilts by a whisper. While outside, observers see nothing but a small change in how a crack exhales. For extra stability, two counter-rotating flywheels inside the core soak up jitters without kicking the body. The world sees a slow, tumbling comet. The heart holds still enough to take sharp readings. Sensors live behind narrow slits and thin windows that look like pits in the crust. One set reads heat across the disk of Earth. Another splits light to learn which gases nibble at which colors. A pair of stubby antennas listen for radio without sending a peep. A magnetometer is mounted on a short boom that looks like a jagged stalk. A tray the size of your palm catches a little of the high air and the dust that drifts this high above the ground. The tray slides shut to keep its sample cold and clean. Each piece is modest. The coverage comes from patience, not size. Navigation favors the quiet life. Before the journey begins, the craft is placed on a path that gravity will deepen into a hyperbolic swing past the Sunday. Small course trims months ahead come from patterned heating rather than obvious thrust. A timer inside sets rolls and tilts that will align windows and slits when the geometry turns right. If a storm of debris threatens, the heart shifts a tungsten slug inside the shell to change spin by a hair and turn the soft side toward the spray. To observers, it is just another wobble in a noisy light curve. Communication is the hardest part under the rules of silence. One answer is to avoid talk near Earth entirely. The core records and compresses data, then waits until the visitor is far past the plane of our orbits. Only then does a pencil-thin beam of light whisper to a relay that lurks in deep cold far from busy lanes. Another answer is even slower. The core carries a small vault that it will release years later on an outbound leg. The vault glides into a distant, quiet orbit and talks only when a coded pattern of starlight appears that no one else would ever think to use. Both options keep fingerprints off the scene while Earth is close. Self-repair must look like weather. The shell can warm two patches and let them sinter back together if microfractures appear. Pores clogged with dust can be cleared by a slow roll that shakes grains toward a trap. If a sensor window darkens, the core can angle that spot towards sunlight for an hour so the haze bakes away. Anyone watching the light curve sees small brightness bumps and chalks them up to fresh crust breaking. The mask holds because the mask is true to comet life. What would such a cautious design reveal to us without breaking cover? Heat maps that sketch seasons and currents, airbands that mark oxygen, ozone, water, and methane with steady confidence. Daily radio rhythms that show clocks and traffic, the flutter of the magnetic shell in solar weather, gentle tugs during the swing that tell the weight of ice and ocean, a powder of dust that carries hints of our rocks and smoke. None of this asks for a call. None of this burns a bright trail. Where might the mask slip? Strong signs would be rare, because the design bakes in restraint. We would look for soft signs that repeat, a narrow fan that keeps the Earth line clear more often than the sun line, minute non-gravitational drifts that peak when Earth sits face on rather than when heating peaks. day length changes that favor windows when our ground arrays are aimed elsewhere. The shell of natural behavior gives cover to many things. Only patterns that care about our position more than the sun's position would risk giving the game away. Now place limits on the table to keep our story honest. Mass is tight. Every kilogram of cloak adds cost and makes small maneuvers harder to hide. Radiation is harsh. The core must live for months in a field of high-energy particles without strong shielding that would alter its look. Dust is sandblasting at orbital speeds. Windows and slits must be small to survive. Steering by heat is slow and cannot save the craft from a sudden hazard. The voice to a far relay must be faint enough to vanish into the general noise of the sky. These are hard constraints. They push the design toward extreme patience. There is an ethical limit too. A watcher that hides in a cometary coat will avoid any pass that risks shedding unnatural debris into our environment. It will not sample in a way that seeds anything into our air. It will not use radio that jams our networks or burns our receivers. The safest rule is to take only what the world already throws away, and shine only in directions where no one in the target system has pointed an ear. Notice how every choice bends toward the same end. Do less, blend more, take the long view. That is why the natural story remains the lead. A small, dusty body that warms and breathes and drifts fits the data with few assumptions, a mask that perfect would be hard to separate from the real thing, even if it existed. The test becomes a long game of patience, not a hunt for fireworks. Still, there is value in holding the design in mind while we watch. It sharpens the questions we ask of the light curve and the path. It helps us write checklists that favor time, repetition, and geometry over hasty claims. It keeps us humble about the difference between strange and artificial. If one day a future visitor does something that crosses the line, we will be ready with methods that grew in nights like these. In the next part, we return to known comet physics that can mimic every faint hint on our list. Crust that breaks in patterns, spin states that wobble and lock, dust fans that track topography in ways that fool a quick glance, gas that vents from shadow by heat stored hours before. By walking the natural playbook with care, we give any remaining oddity a fair and honest background to stand against. Natural comet life has many ways to mimic the soft signals that make us curious. A dusty, icy body warms unevenly. It spins in a slightly messy way. It vents from cracks that open and close with heat. All of this can produce bumps in light, tiny path drifts, and fans that seem to favor one direction for a while and then wander. If we walk through these ordinary causes with care, many faint hints lose their mystery. Start with thermal lag. Sunlight warms the surface, but the subsurface responds late, the way a sidewalk stays warm after sunset. Gas can rush out from a shaded crack hours after the spot last saw the Sunday. That delay makes a jet appear when geometry to Earth is good, even though the trigger was earlier heating. Stack a few of these delayed puffs and you get short-lived increases in brightness that look coordinated with our view but are not. Next, topography. A comet's skin is not smooth. Ridges, pits, and cliffs funnel gas into narrow plumes and block others. As the body rotates, the same canyon can aim its jet toward Earth on certain nights and away on others. If our best images arrive on the nights when the canyon faces us, we see a repeating fan that seems to care about our position. It is only the landscape acting like a fixed nozzle. Spin states add another layer. Small bodies often tumble a little, with two motions at once. Their day length can drift as jets act like tiny brakes or accelerators. These changes are usually tied to sunlight, but the combination of two slow wobbles can make some orientations repeat on a schedule that happens to overlap with our quiet radio windows. This creates a false rhythm that is easy to overread. Consider composition. Not all ices wake the same way. Water ice needs more heat. Carbon monoxide and carbon dioxide can vent in colder zones and from deeper pockets. If a cold jet turns on while the day side is already busy, the total push angle shifts by a few degrees, and the light grows faster than the simple rule of thumb. The result looks like a designed adjustment. It is only the mix of ices taking turns. Now, the phase angle. which is the Sun-Comet Earth geometry. When the object sits at angles that favor forward scattering, dust looks brighter, like fog glowing in low sunlight. A small change in angle can make the coma surge without any change in venting. These phase effects can reach whole magnitudes in the right grains. To a casual eye, surges appear scheduled. They are just the optics of dust. Dust size and shape matter too. Tiny grains scatter blue light more, bigger grains lean red. If a crack begins releasing finer powder for a few hours, the core region looks bluer and brighter. Later, as larger grains dominate, the tone reddens and the brightness fades more slowly. Color swings like these do not need new materials or intent. They reflect the sieve, like way that grains are lifted. Crust physics can offer repeat behavior. Sunlight can sinter a fragile skin that holds pressure beneath it like a weak lid. That lid fails at a stress point over and over as the body turns. The way ice on a pond pops along the same line. Each failure vents, brightens, and nudges the path in the same direction until the crack grows and the pattern ends. Weeks of similar bumps can come from this one recurring fault. There are seasonal effects even on small bodies. If the spin axis is tilted, one hemisphere enters a brief summer as the orbit carries it around the Sunday. Subsurface ices in that half-warm deeper and vent later into the evening. Over a month or two, this shifts the average push and brightens the coma at times that repeat each rotation. The pattern feels intentional when plotted beside Earth's schedule, yet it is only a tilted top under steady light. Outbursts that look sudden can be slow physics reaching a threshold. Amorphous ice can crystallize when warmed enough, releasing trapped gases all at once. A pocket of gas can breach into a void and lift a slab of dust, creating a short storm that settles quickly. These events alter brightness and path without warning and need no guidance. Now turn to the way we measure. Instruments and methods can introduce patterns. Trails in images smear faint objects and can bias the measured center by a hair in the direction of motion. If that smear is stronger on nights when the target is low in the sky, position fits will tilt in a repeatable way. Flat field errors and background gradients can raise or lower coma brightness subtly. Different filters across observatories produce color effects that look like physical changes but are only calibration gaps. Scheduling produces soft biases. Ground telescopes observe when the object is high and the moon is not washing out the sky. Those windows can line up with the same hours each night from a given site. If an observatory has the best weather in a certain season, many of the key points come from the same longitude and repeat the same local timing. It becomes easy to match bumps to our habits without meaning to. Data selection matters. Teams throw out frames with clouds, guiding glitches, or satellite streaks. That is right, but it can leave nights with only the better behaved segments of the rotation, shaping a false smoothness into the light curve. Later, when better coverage returns, normal roughness looks like a meaningful change. Even our attention can bend the curve. When a rumor of an anomaly spreads, more eyes look, and more reports arrive during the very windows under discussion. A stronger stack of data, exactly when people care most, makes a gentle phase effect look like a deliberate alignment. The cure is to keep to a plan set before the excitement. Put these together, and you have a natural playbook that explains most soft hints. Delayed venting, fixed nozzles in the landscape, mixed ices taking turns, scattering optics, recurring crust faults, seasonal tilts, threshold outbursts, and the scaffolding of measurement and scheduling can all produce patterns that feel personal to us. The honest way forward is to model them first, subtract them cleanly, and see what remains. There is virtue in this discipline. By building better thermal models, we learn how crusts evolve. By mapping topographic jets, we understand how small bodies erode. By correcting phase effects, we improve albedo and size estimates. By standardizing filters and calendars, we raise the floor for every campaign. Natural explanations are not the enemy of wonder. They are the workbench that holds it steady. If, after this careful accounting, A handful of correlations survive across many angles and many nights, then curiosity is on firmer ground. A remaining trend that leans toward Earth when the sun says it should not, a spin change that recurs at times that favor listening rather than heating, a narrow fan that tracks our line of sight through changing seasons. These would be soft but stubborn. Even then, the right response is to invite more eyes, more wavelengths, and more independent reductions. In the next part, we will place 3i Atlas alongside the first 2 interstellar visitors and draw a plain table of what they share and how they differ. We will stay with simple ideas, so the comparisons feel like stones you can hold. From there, we will ask what those stones say about the space between stars and about the odds that one day a visitor will cross the line from natural to made. Set 3 stones on the table. The first is long and dark, a shard that crossed our sky in 2017 and left argument behind. The second is a classic snowball from 2019 that raised a clean tail and behaved the way textbooks predict. The third is our current visitor, faint and unfinished as a story. Call them 1i ʻOumuamua, 2i Borisov, and 3i Atlas. Origin first. All 3 rode open tracks that do not loop back to the Sunday. Their approach speeds were higher than anything native objects keep far from the planets, and the angles of their paths pointed from regions with no local family. In simple terms, they came from away, and they did not stay. That is the shared core. Surface behavior splits them. 2i Borisov glowed with a coma and tail almost from the start. Dust and gas rose in step with sunlight. Colors and spectra matched familiar comet blends. Its light curve, while lively, felt like the honest pulse of a natural snowball waking up. 1i ʻOumuamua was the contrast. No clear coma appeared. Brightness swung sharply as it turned, hinting at an odd shape, and the track showed a small drift that did not line up neatly with simple dayside venting. Debate followed because the push seemed too tidy for weak gas, and yet no halo was plain. Early looks at 3i lean comet-like, but patience is still required before anyone speaks in hard lines. Sizes and shapes next. 1i behaved like a small, oddly shaped body, perhaps flattened or elongated, spinning with a slight wobble. 2i behaved like a larger nucleus that shed dust easily and built a generous halo. 3i is unresolved at great range, the usual state for something so distant. The reach of its glow and the total light point to a modest core wrapped in a cloud that thickens with warmth and thins as it cools. Nothing in that picture needs anything exotic. Color and dust, too. I showed the neutral to slightly reddish tones seen in many comets, a sign of carbon-rich grains mixed with rock powder. 1i offered little gas to study, so color carried more ambiguity. Early notes on 3i suggest a dust-dominated profile whose hues do not shout for attention. If that look holds, it favors common materials over rare ices that would swing color in step changes. Motion beyond gravity. 2i's tiny pushes lined up with sunlight, just as steady vents would do. 1i's drift sparked argument, because the push seemed too neat for weak gas, and yet no coma was obvious. 3i's fit will take time to settle. Early position chains rarely lock down small non-gravitational terms. When a stable solution appears, the push will either echo the sun like 2i, whisper a puzzle like 1i, or fade into the noise. Any outcome refines our baseline for the next visitor. Access matters. 2i stayed bright long enough for months of work. 1i moved faster and faded quickly, which is one reason the debates linger. 3i's geometry looks like a middle ground. Access is decent but not effortless. A setup that invites cooperation and shared logs without letting anyone close the book too soon. A pocket guide you can hold. 1 came quiet and odd, no tail and a strange push. 1 came loud and textbook true, with a bright fan and drift that followed heat. 1 comes with a soft glow and a few brisk nights that may settle into ordinary models as the data mature. That line is enough to carry the comparison without heavy terms. What changed in our craft? 1i sharpened curiosity about shapes, spin states, and subtle surface physics. pushing modelers to explore porous crusts, bright and dark patches, and the small ways thermal forces act on stiff, low-mass bodies. It also reminded us that labels are not answers. 2. I delivered comfort and calibration, letting teams test pipelines, compare filters, and set a reference case for interstellar comets that behave well. 3. I is changing cadence more than theory. It is nudging surveys to share faster, amateurs to keep steadier logs, and planners to ready rapid response checklists that can trigger ultraviolet, infrared, and radar support on short notice. What do the 3 say about what floats between stars? The space between suns is seeded with fragments from the birth and death of planetary systems. Shards chipped from young worlds wander for ages. Icy bodies ejected by growing giants drift until chance brings them through a new sky. Most will be small and quiet. A few will be bright and slow enough for careful work. The growing catalogue will tell whether ice-rich bodies outnumber dry fragments, and whether odd, processed pieces like one eye are common or rare. And the odds of an artifact, the background is rich and varied. In a busy background, a cautious scout could hide as a raindrop hides in rain. That does not make such a scout likely by default. It raises the bar for evidence. Any claim would have to rise above thermal lag, topography, mixed ices, phase angles, and the tricks of measurement that mimic intent. The path to such a claim, if it ever comes, will be slow and collective, resting on patterns that survive many angles, many nights, and many independent reductions. There is comfort in that. A high bar keeps wonder honest. Meanwhile, the work that clears ordinary cases strengthens everything else we do. Better thermal models teach how crusts crack. Better coma maps teach how small bodies erode. Better phase corrections sharpen size estimates. Shared calendars raise the floor for every night at the eyepiece or the keyboard. Carry one last picture to bed. 3 stones on a table. One is strange and smooth. One is crumbly and leaves dust on your fingers. One is still damp with dew and not yet fully known. As more arrive, the pile will speak more clearly about what drifts in the dark, and about how often a device might hide among the debris. Whether 3i proves ordinary or slightly odd, it will help shift us from single cases to patterns. In the next part, we will move from contrasts to thresholds. We will define, in plain words, a handful of observable signs that a wide circle could test and agree upon before anyone speaks the heavy word artifact. Thresholds help a wide circle agree on what is interesting and what is ordinary. Here is a plain set of signs anyone can track, and rules for how strong each sign must be before the word artifact is considered. First, geometry-locked drifts. If tiny departures from a gravity-only path lean toward Earth more often than toward the Sun across many viewing angles, mark that as yellow. If the preference persists for weeks, survives independent fits, and remains after standard thermal jet models, raise it to amber. If the drift peaks when solar heating is weak and fades when heating is strong, and this repeats at least 3 times, that is red. Second, a fan that favors our line of sight. If a narrow wedge in the coma keeps its brightest edge near the Earth direction through changing phases, call that yellow. If 2 or more observatories on the same night see the same wedge, and the wedge rotates to keep us in view as the body turns, make it amber. If the wedge holds its aim on nights when the sun sits far to the side, and phase effects predict the opposite, and this holds across a month, that is red. Third, rotation changes tied to opportunity rather than heat. Natural jets speed up or slow down the day length in step with sunlight. If period changes cluster near hours when Earth geometry is best for listening or viewing rather than when heating peaks, that is yellow. If those changes line up with windows when our largest dishes are often free, or when orbits give clear lines of sight and the link repeats, make it amber. If the pattern is forecast in advance and then lands on time, that is red. Fourth, color or spectrum features that refuse the comet playbook. Most small comets show neutral to reddish dust, with gas bands that rise and fall with warmth. If repeated color swings appear without matching changes in brightness, that is yellow. If a stable narrow feature shows up at a wavelength with no known comet gas and it repeats in independent instruments, amber. If the feature tracks with orientation to Earth rather than to the Sun and survives deep checks, red. Fifth, heat that acts like a radiator, not a patch of sunlit crust. Ordinary warming produces smooth thermal maps. If infrared brightness forms a tidy stripe that turns with the body like a panel, yellow. If the stripe's width and temperature stay unusually constant while other areas change as expected, amber. If the stripe schedules its best view for Earth, favored hours and fades when we turn away, red. Sixth, timing that chases our networks. If small brightening steps or subtle bends concentrate during hours when global radio traffic around Earth is lower and the big dishes are in handover, yellow. If those steps skip equally warm hours that fall during our busiest link times, amber. If the pattern holds after blind tests and a control comet shows no such behavior, red. Seventh, responses to predictable probes. When a narrow beam from a deep space antenna sweeps near the visitor by geometry, a natural body does nothing special. If the coma briefly steadies or the light curve smooths during several such passes, yellow. If the visitor tends to be best placed during those passes, more often than chance, amber. If a specific pass is predicted to show the effect, and it does within the stated window, red. No single sign stands alone. The rule is accumulation. 2 yellows do not make a red, but 3 ambers from different categories demand attention. To keep the process fair, the community can adopt a few ground rules. Predictions before verdicts. Claims include near-term checks, so fresh data can verify or erase the hint. Blind reduction. A slice of raw data is shared with teams who do not know the hypothesis. Controls. Every time a normal comet in a nearby patch receives the same analyses. Independent clocks. Results use absolute times, shared ephemerides. Positions and viewing angles come from a common source, public logs. A daily ledger collects yes and no results, so quiet nulls weigh as much as loud spikes. Here is a decision tree. If, after a month, there are no ambers and only scattered yellows that fail their forecasts, the verdict is natural behavior. If 1 or 2 ambers appear but do not repeat, the verdict is natural with lessons for models. If 3 or more ambers persist across categories and survive blind checks and controls, trigger a focused campaign with more wavelengths and perhaps radar. If a red appears and repeats with prediction, convene a formal review panel. What happens in a focused campaign? Infrared telescopes map heat nightly. Polarimeters read how scattered light twists. High-cadence photometry watches spin without gaps. Radar, if range and geometry allow, checks size and shape. Spacecraft teams seek observation slots. Data from all of this flow into an open notebook. Why such care? Because thresholds protect truth and wonder. They keep us from leaping at shadows and keep us from waving away patterns that earn attention. They also build habits that lift the field. The next visitor, whatever it is, will meet a community that knows how to turn soft hints into clear answers step by step. There is a final threshold beyond instruments, the human one. Can we hold our tone when the story heats? Can we share credit and confusion with the same grace? Can we write what we do not know beside what we do? If we can, then even a natural comet gives us something rare. A chance to practice being the kind of observers we hope to be when a visitor truly crosses the line. In the next part, we will follow a night on the mountain and a day in a data room, letting the pace of real work carry the story from starlight to numbers to quiet conclusions a person can trust. Start with cold air and a quiet dome. The floor hums, shutters part, and the telescope breathes while stars sharpen to tiny points. The target sits low, a pale dot against black. The operator reads the list. Exposure time set. Filters ready, guiding on. Short images check focus and pick the visitor from background stars. A dim speck slides a fraction of a pixel between frames. The night begins. Tracking switches so the telescope follows the visitor, not the stars. In each frame, the dot stays fixed while the field smears into thin trails. A set of 10 exposures start. Each is long enough to lift signal above noise, but short enough to keep the core sharp. Between pairs, a small dither shifts the image to average bad pixels and dust. The camera stays cold to keep calibration clean. The clock is checked against radio time. An hour brings a stack. Calibration is applied. Darks subtracted, flats divided, and the sequence aligned on the moving dot. Starlight becomes faint lines that cancel when added with care. The dot grows into a soft knot with a bright center. A curve through that knot shows how the light falls with distance. It is wider than a bare rock and narrow enough to suggest a compact coma. The profile and notes are saved. The object climbs, the air thins, the background improves. Another series begins, with slightly longer exposures to probe deeper into the halo. On each pass, the operator notes wind, seeing, height, and any satellite trails. If it is not written, it did not happen. Near midnight, the telescope turns to standard stars to anchor brightness and color, then returns to the visitor and repeats the sequence. Target, standard, target, blank sky, target again. Close to dawn, the air steadies. The visitor brightens a touch. The set finishes, and the dome closes. Data and notebook go downstairs to a room with red lights and a kettle. Night becomes day. The data room holds screens. A script builds a first light curve. Each point carries an uncertainty bar. Another script measures the coma shape and plots a compass that can hint at a fan. A third script fits the center with sub-pixel care to record the exact position against a grid of background galaxies. That position joins a global ledger before breakfast. Next comes rhythm hunting. A period search looks for a flicker that repeats. A small peak appears near several hours, but coverage has gaps, so it is marked tentative. Another tool folds tonight's curve by the candidate period and compares with the previous week. The overlap is weak. Positions go to the orbit fit. The program compares where gravity says the dot should be with where it is, writing the differences as tiny residuals. Most nights, the residuals scatter around a flat line. Tonight, they lean a little in one direction. A model with a gentle push, aligned with sunlight, shrinks them. A model with a push toward Earth does not help. The note says sunlight term mild. The coma compass shows a faint wedge that points a bit away from the sun. As expected, a check of the angle between the wedge and Earth shows nothing special. The wedge drifts with rotation and does not hold a fixed aim. Brightness is plotted against hours when large dishes on another continent hand over between shifts. No match. Colors from paired filters look normal for dust-rich coma. The inner few pixels in the blue filter are a touch brighter relative to the outer halo, a sign that gas scatters near the core. The effect is small and within ranges seen on many comets at this distance. A spectrum from a partner site arrives and shows weak bands that align with common gases. Midday brings a call with another site. Their night was clouded early, but clear late. A good complement. Their positions agree within error bars. Their light curve shows a small rise near local morning. Phase angle effects likely explain it. Both teams mark the bump as ordinary and plan to watch whether it repeats when geometry changes next week. After lunch, the group builds a control. A known small comet with similar brightness gets the same scripts, the same plots, the same tests against dish schedules. The control shows two bumps of similar size with random timing. The wedge points as solar pressure predicts. The rotation hint appears here too when coverage is sparse. Lesson noted. Sparse data plants, false peaks. Late afternoon, the lead writes the daily summary. Positions uploaded. Light curve shows mild, brightening with phase angle likely. Coma wedge stable in solar frame. No sign of geometry locked drifts. Color within normal range. Tentative rotation hint not significant. Control mirrors small features. Recommendation is to keep cadence and add one longer infrared set next clear night. The summary goes to an open board where many teams post their own. Some nights thin, some rich, but the tone is measured. No one claims a surprise. No one rules out new development. Evening returns. and with it, a quiet pride. The method worked. The sky was kind. The notes are clean. The result is ordinary in the best sense. A steady step that joins many others. If a faint oddity ever stands up, it will be backed by habits born on nights like this. Before sleep, eyes pass the thresholds list on the wall. Drifts that lean toward Earth. Wedges that hold their aim. Spins that chase our windows. Colors that refuse the playbook. Heat that turns like a panel. The boxes for tonight stay empty. The window darkens. The visitor is far along its path, and the long machines of the sky keep watch without us. When the next night comes, the dome will open, the focus will snap, and the quiet work will begin. Carry the same rule up the stairs. Write what is true. Test what is tempting. Let pieces add up. Plans grow from nights like these. When a pattern of careful watching becomes normal, the mind starts to ask for tools that can move faster and see wider. A visitor from another star does not wait for us. It crosses our sky on its own schedule. If we want more than distant profiles, we need ways to meet such guests mid-journey. That means readiness, not rush. It means instruments that can pivot within days, and small craft that can ride standby paths until the alert comes. Picture the simplest ladder. At the bottom are wide-field eyes that scan the sky every clear hour, not just every clear night. Their only job is to catch faint movers early and send clean alerts. Above them sit a ring of telescopes tuned to heat, color, and polarizing cues that reveal grain sizes and gas. A few are on mountaintops, a few ride balloons for weeks above the weather. Their job is to spin up within a day and sketch the visitor's glow in several bands. So, models of dust and vents start solid. The next rung is speed in space. A handful of light probes sleep in quiet orbits that let them sprint with little fuel when a target appears. They carry simple cameras and spectrometers, nothing flashy, only eyes that can close the range and hold a steady view for a few days. Their antennas are modest. Their data compress on board into small packets that a network of ground dishes can catch without strain. The crafts are not designed to touch. They are designed to arrive and watch, then drift away, as softly as they came. Above that rung is the patient net. A relay far from busy lanes waits for faint beams from outbound guests that need to whisper home without lighting the stage near Earth. We do not need to guess who might be sending. We only need to be ready to hear. A long baseline array of quiet receivers, tuned to harmless parts of the spectrum, can keep ears open without adding noise to the sky. Higher still is the learning loop. Each visitor, whether ordinary or odd, feeds the models that feed the next chase. The shape of a light curve tonight guides where a quick probe points next year. The way a coma brightens at certain angles tells a new camera to add a filter we did not think we needed. The loop closes when results and code live in open archives that students and clubs can use. The more hands that practice, the steadier the field becomes. A plan like this does more than serve curiosity. It strengthens the calm parts of our nature. Precision replaces panic. Discipline replaces rumor. A quiet visitor thus becomes a teacher twice over. It brings us physics, and it brings us habits. Place this against the Black Forest idea. In a quiet galaxy, the safest voice is a whisper, and the safest action is patience. Our best answer to such a world is also patience, paired with skill. We prepare to meet the natural case with grace, and the extraordinary case with care. If one day a true artifact crosses into daylight, we will have built the ladder that reaches it, and a culture that can carry the weight of knowing without breaking itself in noise. There is a softer gain that touches the night within us. Long watches teach the mind to move slowly and see clearly. A person who keeps a simple notebook learns that thoughts have seasons. Hints appear, grow, and fade. Most do not flower. A few do. The lesson travels from the eyepiece into the day. You begin to plan your work in small steps. You learn to set rules before excitement. You accept that the honest answer many times is ordinary, and that ordinary, held with care, is beautiful. Hold also the dose of humility that the sky prescribes. Interstellar space is not empty. It carries shards and snowballs from rooms where other worlds were built. These pieces drift for ages, and then, without announcement, slide through our sunlight. We mark them with neat names. We fit curves and measure colors. Yet, beneath our labels is the quiet fact that we are meeting the larger process that made us two: dust, ice, heat, gravity, and time. Whether a device ever hides among the debris itself is a story worthy of being told in a low voice. Return now to our visitor. The ledger is growing. The nightly boards fill with points and notes. Patterns rise and fade. The thresholds stay unlit. This is fine. Calm endings are still endings. If the object keeps its simple course and writes no strange lines in the air, it will leave us a better craft and a steadier esteem for the honest work it took to reach that calm. Before we close, set a few hopes on the shelf. May wider surveys turn up many more interstellar guests, so that single cases yield to populations. May early alerts arrive with enough margin that quick probes can meet a few on the road. May the tools that serve this work also guard our own neighborhood by finding faint rocks on bound paths in time to matter. May open logs and open code remain the norm, so trust grows with skill. Then let the room dim. Picture the visitor far beyond the last planet now, a pale seed drifting back into starlight. Our instruments have said their piece. Our notebooks have their pages. The thresholds hang quiet. The questions fold for the night, not in defeat but in rest. Tomorrow may bring another hint, or nothing at all. Either way, the habit remains, and the habit is the treasure. If somewhere a cautious watcher truly rode past in a comet's coat, it learned what it came to learn without harm. It saw our warmth and our clouds. It felt our magnetic shell flutter and heard our soft radio hum. It weighed our oceans with the faint tug on its path and tasted the dust that lives above our air. It left without a ripple we could name. Perhaps one day, long after we are ready, a second pass will draw closer. Perhaps not. Silence is also an answer. For now, rest in the simple closeness that a night of steady work brings. A small light crossed the dark. We watched well. We told the truth as we found it. We added one careful page to a story that will outlast us. The forest remains, deep and quiet. We walk its edge with respect. There is one more layer to lay down before we part. A layer about how we carry nights like these into our wider living. The sky gives lessons in small doses, and those lessons, when kept, shape the kind of people we become. A quiet interstellar visitor is a teacher that does not speak. We do the speaking by the way we look, record, and share. The first lesson is steadiness. A person who keeps to a simple plan learns to trust ordinary steps. Wake, set the target, write the times, compare the curves, post the notes. Nothing in that list is heroic. Everything in that list matters. It is the same in a studio, a lab, or a kitchen. The great projects are built on ordinary lists, done on ordinary days. If 3i Atlas taught you to keep a notebook for a month, it already made your world a bit stronger. The second lesson is clarity. We chose plain terms on purpose, not because hard language is wrong, but because clear language keeps the mind honest. When you say hyperbolic path, you say it means the visitor will not stay. When you say non-gravitational push, you say it means sunlight turned ice to gas, and gas nudged the body. Clarity like this cuts through the fog of hunch and rumor. It lets anyone test the same idea, which is the heartbeat of trust. The third lesson is kindness to uncertainty. For many weeks, we said not yet to drama, not yet to verdicts, not yet to the tempting headline. That posture is calm, not timid. It protects truth, and it protects the spirit. Most puzzles need time more than noise. If children learn that we do not know yet is a full sentence that carries dignity, the next generation of watchers will be both braver and wiser. The fourth lesson is attention to scale. A pebble far away can move a culture up close. A few photons on a sensor can bend a week of work. A faint outburst in a light curve can send hundreds of eyes to the same window. From this, we learn that small things, tracked well, change large things, and we build systems that honor tiny signals without letting them rule us. Balance shows up as a habit, not as a rule. The fifth lesson is patience with endings. Most nights end without crisis or revelation. You close the dome, you wash a mug, you post a tidy line in a quiet thread. This is not failure. This is the true shape of real work. The big moments, when they come, sit on top of these calm endings, like a bird that trusts a firm branch. If we honor the calm, we earn the thrill. Lay these lessons beside the story we told. A visitor from between the stars passed through our sunlight. It brightened when warmed and carried a soft halo that fit what we know. We checked for signs that would tie its behavior to our position rather than to the Sunday. The signs did not rise above the honest background of ice, dust, light, and time. We built thresholds and they stayed quiet, which is itself a result with weight. We prepared methods a little better for the next case. We grew a bit as a patient community. Now tilt the view forward. What might your own nights look like because of this one? Perhaps you keep a small ritual, a 5-minute check on a public plot in the evening. Perhaps you and a friend agree to run a weekly summary of news in plain language for people who are curious but busy. Perhaps a teacher in your town starts a night lab where students learn to fold data, not just read about it. Perhaps a maker you know designs a tiny open receiver that clubs can build to listen for harmless parts of the sky without adding noise. The seed is simple. The fruit can be many. There is room, too, for a softer art to accompany the charts. Painters have always turned stars into color. Writers have always let a night field into their pages. Musicians have always heard the slow meter of planets. If a quiet comet can carry us to sleep while we learn, it can also carry a melody or a sketch. Wonder that moves the hand to craft does not compete with science. It keeps science company. Return, one last time, to the Black Forest idea that framed our question. In a cautious cosmos, light is risk, and quiet is survival. If that idea is even partly true, then most watchers will be gentle, and most clues will be faint. The right answer to faint clues is not to strain your eyes until you see shapes that are not there. The right answer is to build better eyes, wider logs, and slower hearts. That is what we practiced. That is what we can keep. So the visitor fades, and we let it go without forcing it to be more than it is. We thank it in the one way that matters to the night. By learning from it, we learned to share faster and with more care. We learned to test our own leanings with control cases. We learned to hold a hypothesis politely. Like a guest coat, we will gladly return at the door if the evening does not call for it. When sleep comes, let a few simple pictures drift across the mind. A pale dot held steady while stars turned to lines. A compass plot with a small wedge that followed the sun as it should. A light curve that rose and fell with angles we could draw on a napkin. A checklist with boxes left empty, not for lack of courage, but for respect for what the sky showed. Thank you for walking these steps together. If nights like this feel good in your hands, support this quiet work the easy way. Tap like so others who crave calm, honest journeys can find them, and subscribe so the next late-night story arrives at your door without fuss. Small clicks carry real weight for a small channel. They help us keep the pace slow, the tone steady, and the craft improving. Now rest. The window holds its dark. Somewhere beyond the last planet, a seed of dust and ice drifts on. We did not waste its visit. We left a clear trail for the next pair of eyes. The forest is deep. Our steps are light. Tomorrow, another page begins. Let us gather the threads and lay them in a simple frame you can hold in the dark. A faint traveler from beyond our sun entered the map of our nights. We asked a cautious question with a calm voice. Could 3I Atlas be only a small natural comet? Yes, easily. Could it also be a quiet watcher wearing the mask that nature provides? Possibly, but only if it never steps outside ordinary physics. Between those poles sits the honest middle, where most truth lives. We watched, we tested, and we learned how to see more clearly the next time a stranger crosses our sky. Begin with what stayed firm, The path was open rather than looped, which means the visitor will not remain. The brightness rose as warmth rose, with bumps that fit the behavior of vents and dust. The soft halo around the core matched what sunlight does to porous ice. The tiny deviations from a gravity-only track were small and, when modeled, leaned toward the sun the way dayside jets usually do. Fans in the coma pointed as solar pressure predicts. Color stayed within normal dust ranges. In plain words, the sky offered no hard reason to raise an alarm. Set beside that firmness, the posture we practiced. We wrote thresholds before we went hunting for signs. We used control cases to teach our eyes how much ordinary nights wiggle. We made predictions and asked the next round of data to agree or disagree. We invited other teams to reduce the same frames without being told the preferred story. We welcomed nulls. This posture is not drama. It is the quiet muscle that lets a community handle a surprise one day without tearing itself. Now return to the question that carried us here. Could 3i Atlas be watching us? If a careful civilization exists and follows the logic of the Black Forest, then the safest probe would wear a coat of dust and ice, steer with thermal breaths, and time every tilt to look like sunlight did the work. Under that mask, a tiny craft could map heat, read air, taste dust, listen to radio haze, and weigh our oceans by its own faint speed changes. All of that is possible in principle. None of it requires a loud signature. So what separates possibility from claim? Not a single bright event, but a stack of soft patterns that repeat across angles, nights, and instruments, despite every natural model we can throw at them. Drifts that prefer Earth over the sun again and again, a narrow wedge that holds our line of sight across seasons. Rotation changes that line up with opportunity rather than heat, and do so on a schedule called in advance. A thermal stripe that acts like a radiator rather than a rough patch, a spectral scab at a place where no comet gas should sit, seen by several eyes. If such a stack ever appears and survives patient attack, the word artifact will not feel heavy or rushed. It will feel earned. What have we gained even without that stack? Better thermal models that tell us how crusts break and heal, cleaner phase corrections that sharpen size and albedo, shared calendars that spread work and reduce bias, faster pipelines that turn alerts into coordinated campaigns in hours rather than days, open notebooks that let students and clubs trace the path from photons to plots. These are the quiet riches of a calm season under the stars. Carry forward a short charter for the next time. Watch often enough that early alerts are real early. Keep a few simple spacecraft on standby paths so a close pass can be met rather than only waved at. Build receivers that can listen without adding noise. Write thresholds in advance and keep them public. Fund the unglamorous parts of the system because they are the parts that turn single detections into lasting knowledge. Carry forward, too, a personal charter. Keep one small practice that trains your patience. Read a plot each evening and write one line about what moved and what did not. Say not yet when a story tempts you to say more than the evidence can carry. Explain one hard term each week to a friend in words that anyone can hold. These habits make you a steadier partner to the sky. The title that brought us in asks a question. Could 3i Atlas be watching us? The clean answer tonight is that we found no sign that demands that reading, and many signs that fit quiet, natural comet life. With that said, the question itself was not a waste. It sharpened our view. It taught us to separate what must be from what might be. It made us better at turning a passing light into a lesson we can keep. There is comfort in endings that are calm. A faint visitor arrived, warmed, and glowed. We followed with care. We set aside shapes that were not there. We added pages to a shared ledger and left clear tracks for others to walk. If a different visitor one day crosses a line that this one did not, our readiness will owe much to nights like these. Hold a final picture as sleep nears. A dark field, stars as tiny pinpricks, and one small blur that slides a fraction of a pixel while the clock ticks. In a room somewhere, a notebook closes. The threshold's list on the wall has empty boxes. A kettle cools. A message posts to an open board with a steady tone. Outside, the quiet machines of the sky keep their long watch. Far away, at the edge of sunlight, a modest seed of dust and ice turns and drifts on, carrying nothing that needs a name beyond the one we gave it. Thank you for sharing this slow journey. If calm, honest nights like this help you rest and think, tap like and subscribe so the next long drift finds you. Small actions make it easier to keep the pace gentle and the craft careful. Beyond the last planet, the forest is deep and quiet. We will be here, listening with soft steps, ready for whatever rustle the leaves choose to share.